soil, gravimetric water content, water potential for soil. Here's the relative water content for a leaf, and 1 over the water potential at these relative water contents. This is a pressure volume curve. Through analysis of this curve, we can get an estimate of the apoplastic fraction. That's for next week. But actually, for this leaf, it's about 18%. This point right here is the apoplastic fraction. Don't worry about that now. We'll get into that. Great detail. So, I mean, it's possible to do it. It's possible to do it. But again, it takes time, and you have to really want to you have to really want to do it, to put the time and effort into making it. And so there aren't a lot of these types of measurements that are made. But I mean, conceptually, you can see that it's an important consideration, especially since these apoplastic fractions can be quite large. All right. We can also use a psychrometer, a special chamber, to measure water potentials of leaves in situ. And here's a picture of one, a blurry picture of one, so I brought in a real one so you can see. This is also available from Westcor, and it's to measure water potentials in leaves in situ. So the idea is you have a leaf still attached to your plant, and it can slide into this little slit in this device. So you slide your leaf in there, push this metal thing down against it, which has a thermocouple in the end of it, tighten it down, and now you've got a sealed space with a thermocouple in it and your leaf at making the bottom of that space. And then you let things equilibrate and measure a water potential. Good idea, right? Nice idea. You know, it's a good enough idea that Westcor is able to sell these commercially, make money doing that. But you have to be very, very careful when using such a device. After all, some consideration. This little piece of the leaf inside the chamber now is in the dark. The stomata closed. When the stomata close, the transpiration rate goes way, way down. That may alter the water potential of this part of the leaf in the chamber compared to this part of the leaf not in the chamber. Sure.
What is the time, like what's the rate of closing of a stomata?
Yeah, so it depends on species and stuff, but on the order of a minute,
Seconds?
couple of minutes.
Okay.
Yeah, a minute or two. It's much shorter than the time it takes to equilibrate the water potentials between the sample and the air.
Okay.
It's short. It's way shorter than that. So it can be problematic.
Okay.
Yeah. Another consideration is that the idea is that this can be used where your plant is growing, right? And typically that's not in a lab, in an air-conditioned lab, right? Usually, sometimes it is, but typically not. And thermal gradients cause a problem. So if you take this outside and use it outside, and if the sun is shining on this side of the block and this side in the shade, you'll have a gradient in temperature through this device. That can cause problems with your measurement. So thermal gradients have to be eliminated. Typically how, let's see, I think this is on the slide. Typically how people use this is to go up to the leaf before the measurement and abrade the surface of the leaf with carborundum powder to remove the cuticle. After all, the waxy cuticle is what is in large part responsible for resisting water loss from the leaf. You can abrade the waxy cuticle without tearing up the epidermal cells if you're very careful and have practiced for a while. And then when you seal up that piece of leaf in the chamber, you reach equilibrium much faster. And so the water potentials don't have as much time to change on this part you're measuring versus this part up here. Also, these things tend to be enclosed in styrofoam and mylar, and you know, you end up with not a thing this big, you know, the size of that, but a softball or volleyball kind of shape that your leaf is sticking into that you're trying to make your measurement in. So that also can be just practically a problem with making the measurement.
How do you choose the leaf on the plant? Like-
So what are you interested in? What's your question? You know, how you choose the leaf is going to depend on what question you're trying to answer. So if you're looking at gradients within the plant from the bottom to the top, then you pick all the leaves, you know, as you go up. If you're interested in transpiration from the canopy, I would start with leaves fully exposed near the top of the canopy. A lot of times people will measure the most recently fully expanded leaf at the top of the canopy as being representative of the canopy. But that's representative of leaves in that position and may not represent shaded leaves further down in the canopy. So it depends on what question you're trying to answer and why you're making the measurement as to which leaf you pick.
And you have to do this while the leaf is still on the plant?
Well, with that device, yeah, that's the idea, to do it while this leaf is still on the plant. I mean, it's a great, it avoids this problem of excising the leaf and losing water before you make the measurement, because you never have to take the leaf off the plant. But it brings other problems with it, keeping the temperature gradient low and having very long equilibration terms, and changing the water potentials in different parts of
I was
the.
just wondering if you worked with Lycor before for the
Yeah.
6800, because you mentioned like this instrument doesn't have, like once you put the leaf inside, basically like there's no light, but then I know that Lycor have that product where they, you know, use LED
Yeah,
and,
yeah, yeah.
you know,
Yeah.
I don't know, what do you think about that? Is it like?
I haven't really thought about it a lot. I've worked with Lycor a lot since I started in grad school here in when did I start? I don't want to say, many years ago. I've worked with them. In fact, now they sell the 6800. Before that was the 6400. Before that was the 6200. Before that was the 6000. I worked with the 6000, developing that when it was still prototype, when I was in grad school. And so I worked with them a lot. As far as having lights in there to keep the stomata open, I don't think it's a big enough problem to really go into that much detail to make that kind of measurement. I think it's other issues are a bigger problem. In fact, losing water between excising the sample and making the measurement. That's a far bigger problem than the stomata closing in the dark, I think. Lycor, we're fortunate to have Lycor here in Lincoln, Nebraska. You know why it is here?
I think there's
Students from.
What?
Because of the universities.
Yes.
From UNLA.
Why? Yeah, because the owner, Bill Biggs, was a grad student here at UNL. In fact, in my building in Kieselbach. He was a grad student working on measuring light and measuring photosynthetically active radiation, PAR. And that was their first sensor that they ended up selling, was a sensor that measured PAR, just the PAR part of the spectrum, not the whole spectrum, but just the PAR part. So he worked on that in grad school, and in doing that, had this idea to make these sensors and made his own company, and you know, it's taken off from there. So we had some of his very, very old sensors in our building. They were really, you know what the sensor looks like now, it's about, the quantum sensor is about, what, this big around and this tall. He started out much larger than that. And, anyway, Bill Biggs worked with Max Clegg and Jerry Miranda and developed those light sensors. And then the leaf area meter was another one of the first instruments that they developed at Lycor. And then they just, they've been fortunate, I guess, in what they've done. They're very interested in working with researchers in the field. So if your research involves any of their equipment, they're very happy to talk to you about it. Go out to the factory, talk with them, bring up problems. They're very accommodating that way, and it's a good resource too. Anyway, you always see them at meetings, like the agronomy society meetings. They'll be there. They'll be at AGU. They'll be at the ecological society meetings. They really do keep up with the cutting edge of plant research. But they don't make water potential instruments. They make mostly, one of the things they make are gas exchange. They're getting into fluorescence now, too. Chlorophyll fluorescence. All right, so leaf in situ spectrometers are also useful. So in summary, we can measure the total water potential of excised tissues, the total water potential of a leaf in situ, or of soil samples, either of samples taken out of the soil or in situ with using thermocouple spectrometers. We can also measure osmotic potentials of solutions, calibration solutions, or juice that we've squeezed out of the plant somehow, and get at osmotic potentials. When making these osmotic potential measurements, we have to be careful to correct for the apoplastic fraction. One way of determining apoplastic fraction is through pressure volume technique, which will come next week, and a very useful machine. So I don't know, you want to see this thing? You can pass these pass them. I haven't gone into exactly how to use it. It doesn't really matter for our purposes now, although I would like to spend time doing that, but we've got other places to go, other things to talk about, especially since this machine, you can't buy it anymore. Okay. So, again, in review, I harp on this because it's quite important, but and I think if you can understand how a thermocouple cycrometer works, you're developing a good understanding of plant water. So remember, we seal up a sample in a small chamber, let things come into equilibrium. At equilibrium, the total water potential of the sample is the same as the air. The total water potential of the air is proportional to the relative humidity in the air. And for a thermocouple cycrometer, we let water evaporate from that thermocouple junction. That gives us an output that's proportional to the relative humidity of the air. For a chilled mirror type cycrometer, we chill the mirror off until we reach the dew point, because we know the dew point and the dew point of the air and the temperature of the air. We can relate that to relative humidity or to vapor pressures and calculate water potentials that way. And oftentimes we need to use a series of calibration solutions that we know the water potential of. We get that from the top. Okay. So that's the summary. Decagon Devices is a company in Pullman, Washington. also the home of a university, Washington State. Also, people from Washington State founded this company in Pullman, Washington. They sell water potential measuring equipment. Westcor is in Logan, Utah. You know Utah State in Logan, Utah. People from Logan, Utah were the ones that formed Westcor initially. And they also are interested in water potential. They're part of a big medical group now. Decagon, I'm not sure who they're part of anymore. Okay. Campbell, you know Campbell Scientific? Have you heard of that company? Also in Logan, Utah? Yeah, so Campbell Scientific, many of the people that founded these companies and Campbell Scientific are named Campbell. Just for your information. Okay, anyway. Galen Campbell is a big name, you may have heard. He's published. Okay, let's go on to something totally different. Totally different way of measuring water potentials. And I take it from this book, Irrigation of Ag Crops. Ted Chow has a chapter, I've already given you this reference, Measurements of Plant Water Status. There are a few pages in this chapter that discuss the so-called Shardakoff technique for measuring water potential. It's in here somewhere, in the middle of this book somewhere. Shardakoff method. All right, so let me talk about Shardakoff method. Not very well known. Doesn't take expensive equipment. It's relatively easy to do. And here's how you do it. We take a series of test tubes that are filled with sucrose solutions of known water potentials. All right, so, and we use Van 't Hoff to figure out how to make these solutions up so we know their water potential. So let's assume we've got a sucrose solution here that has a total water, or an osmotic potential, total potential of -0.8 megapascals. This one is -0.9, this one's -1, and this one's 0.1, -1.2. Okay? And we've got 5 solutions. So you have to know something about your unknown sample, namely what kind of range of water potential you expect to have, so that you can make up the appropriate range of solutions. So let's just assume this is it. Okay. Now, we go to our, let's say we want to do the total water potential in a leaf. So we go to our leaf and cut up a bunch of little pieces of that leaf and put them in smaller tubes. So here's one with a few pieces of cut up leaf in it. Forgive my artwork, you know. I should spend more time, be more creative, right, than just using whatever it was to use to make them. Put a few pieces of cut up leaf in a small tube, and then take a small amount of one of the standards and bathe these cut up sections with that standard solution. Okay, so at the end then, for this case with 5 of these, we have 5 small tubes with some of the solution in each of those tubes. A different one in each tube. Now ask yourself, we let things come to equilibrium. Ask yourself, what happens? Which way does the water move? Well, it depends on the water potential. Let's assume this was -1 megapascals. And let's assume that our leaf sample has a total water potential of -1.2 megapascals. Water is going to move from here into those cells. Right? Remember this, I need more than one of these. Remember we had our equation for water movement across a membrane. Was this. this reflection coefficient for sucrose is close to 1 for plasma membrane. So this is about equal to the total water potential difference across that membrane from inside the cells to outside. Right? So if this is minus 1.2 inside, minus 1 outside, the water will move into those cells. All right, so you let that happen. Then a little bit later, once things have equilibrated. Okay. Once things have equilibrated, if the water has moved from the solution into the sample, this remaining solution out here is more concentrated. Because we use sucrose, since it can't cross the membrane, and this solution will be more concentrated in sucrose. Higher concentration means it's denser than it was before. And its density has increased. Density is collective property, just like water. So this, after equilibration, if this was minus 1.2, this was minus 1, the water moved in, the solution out here is more dense than it was before. You take a small bit of dye and add it to this solution. I couldn't make this blue for some reason. But imagine if this was dyed with a blue dye. Enough so that you can see the color of it, but not enough to change its water potential. And there are dyes that work that way. Okay? After equilibration now, we take a droplet of this blue liquid in the tube and use a pipette to reintroduce it into our standard that we started with. And we place it right here in the middle. Then we take our pipette out and watch what happens to this droplet. What's going to happen eventually is going to diffuse and you won't see it anymore. But initially, what happens is it either rises or falls depending on its density relative to the density it started with. In our case, if the water moved from the solution into the sample, the remaining solution got more dense. We dye it blue and stick it back in here. This droplet will begin to fall in this tube until it disperses and you can't see it. When you see that droplet falling, then you know, the water potential of my sample was more negative than this solution. And if you do that for all of the solutions, hopefully you find one where it falls, one where it rises, and one where it just sits there in the middle and doesn't do anything. That's the total water potential of your sample. Easy. Just need tubes, sugar, pipette, razor blade. You can do it. You don't need a big expensive machine. I don't need anything. That's a clever technique, I think. How do you like it? One big precaution, as you may surmise, one big precaution is losing water when you excise the tissue and before you place it into the little tube with the solution. Right? So water loss from that time period it takes can be a problem, just as with the cyclometer technique. And you want to minimize the equilibration time because that living piece of leaf in the water is living and things can change in the cells. Those changes can lead to changes in water potential. Another problem that this has, and it shares with taking leaf punches for a cyclometer, is, if you think about it, when you cut the leaf, all of the cells along the edge of that tissue that you're using have been cut. Their pressure potential now is 0. They have a different pressure potential. They have a different total water potential than the rest of the cells in the sample. So you want to minimize the ratio of the cut part of the sample to the total volume of the sample. And that tends to be why people use discs, because that, you can't get any more minimum than that. So that, you want to, I don't know if that, oh, there we go. That's number one. That ratio is, but you know, you have to do that to use the technique, so you can't avoid that problem. All right, and there's this, okay. Shardakoff method, relatively easy, doesn't require expensive equipment, but nobody uses it. Why? I don't know. That's the question Ted Chow asks in there. Why doesn't anybody use this technique? He uses it. I don't say nobody, no, very few people use it. I think probably because just nobody knows about it. Not many people know about it. Now, he published it in this big book, you know, and he's got 2 pages out of 1,218 pages that talk about that. And that's, yeah, 2 pages right here. 1, 2, you know, I don't know. 1948 it was published. Let's look at, see what journal it was published in. I don't even know. It's probably in Russian. Shardakoff. Yeah, it's in Russian. Who speaks Russian? Anybody? So I don't know this journal, but here, if you want to look it up. I don't know, you probably have to get an interlibrary law. It's 1948, it's in this one. This is obviously romanization. No. It looks like 160. So that's 1948. So I'm not familiar with this journal. Kind of looks like maybe it's Proceedings of the National Academy or something. But
I have a question. Why don't you use the entire leaf?
you could use entire leaf. I mean, for Shardakoff or
Yeah.
for.
Mhm.
You know, so for Arabidopsis, maybe you can use entire leaf, or leaflet, or something like that, or, you know, something like honey locust, you know, has leaflets that are amenable to that. And it would not be a problem, you could use that. But for maize leaf, you know, what are you gonna do, get a barrel of sugar water, put it in there or something? Yeah, I think just because of practical reasons, that is the only thing. There's nothing that prevents you from using an entire leaf. Okay? Nobody knows. All right. In the 10 minutes we have left, let me talk about pressure potentials a little bit. Okay? How can we measure pressure potential? We can use a thermocouple cycrometer or a pressure chamber to get the total water potential of our tissue, freeze it, thaw it, measure the osmotic potential using a cycrometer, and then get the pressure potential by the difference between those two measurements. That's the most common way people have of quantifying pressure potential. As I said last time, it works, but any errors you have in these measurements are going to show up in this measurement. So it's not entirely satisfying. How do we measure pressure potential? We can use a pressure chamber to make a pressure volume curve. Okay, haven't talked about that yet, but that's coming. I'll explain that in the future. That's a good technique, but it takes a long time. A third technique is to directly measure the pressure in a cell by sticking a probe right into it. And here are two references. These are the first two references that talk about using the pressure probe, as it's called, the pressure probe technique for measuring water relations of cells in higher plants. Okay, so this group in Germany was amongst the first people to make these types of measurements, and they started with this plant called Mesembryanthemum crystallinum. I don't know, it's native to South Africa, but it was used, or it is used a lot in San Diego on the sides of the road, just to, you know how here they plant tall grass prairie plants on the side of Highway 2 or something driving through. In California, they like to use this ice plant because it's very drought tolerant and grows well. And it has big cells that are amenable to kind of a crude hypodermic needle getting shoved into. That's why they first used this. But the technique's been refined, and now it can be used to measure very small cells too. So what it consists of is a capillary, a microcapillary. So a thin glass tube that's hollow, that you can poke right into a cell. And you have to look through a microscope to make the measurement. And basically you poke it into the cell. Since there's a higher pressure here than outside, if the pressure in, typically this tube is filled with oil and stuck into the cell. If this oil is at atmospheric pressure, what happens is the stuff in the cell squishes out and pushes this oil-water interface out this way. And then what you can do is increase the pressure on this oil by doing whatever you do and force this to go back to where it was when you poked it. And the amount of pressure it takes to do that tells you the pressure potential in the cell. It works. So initially, this was used with Mesembryanthemum. Well, actually, even before that, they used big algal cells. But then it was used in ice plant. But now you can use it in standard size cells, 50 micron diameter cells. You can make these types of measurements. You can also not just measure the pressure potential, but it can be used to determine the modulus of elasticity of the cell wall, because by varying the pressure, you can get the relationship between the pressure and the volume of the cell. And that tells you something about the mechanical properties, the elastic properties of the cell wall. It can also be used to measure the hydraulic conductivity of the cell membrane cell wall complex. So it's a very useful technique, but it only measures one cell at a time. And a maize leaf may have 150 million cells in it. What are you going to do? Which cell is represented?